Welcome, everyone. I'm Sanjary. I'm working for Booking.com in Amsterdam. And, oh, sorry, it froze. Yeah. So, my talk is, as you can see, Lifecycle of kubectl command. Here I'll show you how we hardened our Kubernetes setup with automation and how that gets reflected throughout the lifespan of a kubectl command. So let's have a quick look at the agenda of the talk. First, we will see the different multi-tenant Kubernetes cluster architecture we have in Booking.com and the usual deployment workflow that our developers follows. And then we will see the challenges that we faced during managing this multi-tenant on-prem clusters and the solutions that we came up with. And also we'll see how we automated all the solution for all the multi-tenant clusters we have across our infrastructure. Then we will see how these automations are leveraged by the lifespan of a single kubectl command with an example. And if we hopefully get time, we'll go through a Q&A session as well. So let's begin. So let's have a look first, the different cluster architecture we have. So currently, at this moment in Booking.com, we run tens of multi-tenant Kubernetes clusters, where we categorize these clusters into 3 environments, basically. The first one is the dev environment, where the developers actually hack into their prototypes and new ideas. Then we have the staging environment, which resembles the production environment, but is used mostly for testing purposes. And then we have the production clusters, where the application runs and serves the production traffic. Now, we'll look at the usual deployment workflow on these clusters in every environment. So the workflow is very simple. In each environment, we have 2 types of clusters now. One is application type. In the application clusters, the workloads are actually run there. The pods, deployments, all these workload type of objects are created in application cluster, and then they run there. And we have a separate type of cluster called management clusters. And in this management cluster, devs actually go and deploy their application with our in-house built multi-cluster canary deployment solution, Shipper, which is a Kubernetes native way to deploy in multiple cluster, route traffic, and shift capacity, and all these things. So our developers just go to management cluster and then tell Shipper to deploy it across our fleet. And Shipper then deploys the application across multiple clusters. If you want to know more about Shipper and the workflow, you can read more about Shipper here. Now, the challenges that we faced during managing this multi-tenant cluster, because as you saw, we have different types of clusters in our infrastructure. Every cluster has to maintain a consistent workflow, permissions, and configurations, right, in every namespace. So each cluster actually shares the same namespaces so that we can maintain the deployment workflow in a smooth way. So the challenges that we faced initially was the project management, because multi-tenant cluster means multiple service owners and deploy their multiple projects in these clusters. And we need resource isolation, which gets solved basically by using Kubernetes namespaces, because that creates the resource isolation. But then comes the resource management, because it's a challenge because different projects has different types of requirements. Some requires more resources, more CPU, more memory. Some require less, right? And we handle such cases using Kubernetes native resource quota object that actually acts as a safeguard so that one project accidentally does not consume entire cluster resources. So resource quotas actually help us achieve that. Then we face the challenge of providing auth management or maintaining the auth management, because in all of our clusters, we want to maintain the same auth protocol and auth pipeline so that users can just go to our management cluster and deploy the application without thinking they have permission in every cluster or not. That just works because we have a consistent auth pipeline across all clusters, using Kubernetes role bindings and the Kubernetes RBAC, and using custom auth webhooks. Then next challenge came is config management. Different organizations have different requirement for the application to run with certain configurations, right? So the way we propagate these configurations is using config maps. And these config maps are injected in every namespace when the namespaces are created. And finally, the validation and safeguards of the resources that are being created. And we achieve that using admission webhooks from Kubernetes and pod security policies, which are also known as PSPs. Using these, we can ensure a secure environment for your workloads to run. Now, these solutions at a glance may seem a bit simple to create for one cluster or a couple of namespaces. But when your cluster increases and when these projects running on your clusters increases, because right now in our tens of clusters, we run almost 1,000 of services in production. And at that point, it becomes more challenging or toily for the admins to maintain those clusters. And this is exactly the point when we need automation to solve all the problems, because doing them by hand is not feasible by that time anymore. The way we tackle that is using a workspace provisioning, which takes care of automating all the solutions that I discussed in the previous slide. So the automated workspace provisioning works with three main components, which is the first one is service catalog. This is something that we built in our company, and the service catalog is just a catalog where before deploying any new service in Kubernetes or any new project, our developers actually registered that service or the project in service catalog so that they can maintain an ownership information, and service catalog just keeps track of the projects that are created and the ownership meta information there. Then the next thing is the booking IAM we have. This is the identity provider for all of our users in the company, which is kept in sync with the service catalog so that it knows which user has permission to which project or which user is admin of which project. This is just keeping track of the different projects we have. And then we have a custom namespace controller that actually does the heavy lifting, and it does the automation for us based on the projects created or kept in or registered in service catalog. And now we will see how the workflow works. So first, our developers create a project in the service catalog, and at the same point of time, our identity provider gets synced with the service catalog with the information for the ownership, like this user has created the project, so this user is an admin of this project now, right? And then what happens after that is the namespace controller that I talked about in the previous slide runs in every cluster we have that keeps a watch on service catalog, and then whenever it figures out there is a new project created, that namespace controller in the local Kubernetes cluster creates these following resources. It creates a namespace for that project to be deployed on. It creates a role binding for all the users who will have access to this project. It will actually assign a group, not static users. In the role binding, we'll see that later. It creates a resource quota object, which actually acts as a safeguard for all the resources to be created in this namespace. It also creates limit ranges object, which is a Kubernetes native object that defines the default CPU and memory request and limits for every container if the users do not provide by themselves. Also, it propagates some our org-specific configuration to every namespace that gets created, and the applications that get deployed in these namespaces can make use of these afterwards. Now, we will see how the lifespan of or lifecycle of a kubectl command actually leverages the automation provided by the previous workspace provisioning workflow. So, for that, let's take an example for a simple pod.yaml. It's just a simple busybox pod, which we will see will get created in a namespace called byterental, for example. And this will run the busybox image with image pull policy if not present. And for say, a developer now will run kubectl create-f on this pod manifest object, right? So what happened actually in this case? First, the user or developer runs the kubectl command or makes a REST API call to the Kubernetes API server. And then the kubeconfig file that we use looks any other kubeconfig file that everyone uses, but instead of using static token or certificate for auth, we actually use the kubectl exec credential plugin. As you can see in the users field, there is no credentials there, and instead it has a command field that has a path to an executable, which is supposed to generate a token for every kubectl command someone runs. And after making a kubectl command, this command field's executable actually is invoked by kubectl itself internally, which we wrote, and that actually generates a custom token that our identity provider understands. Then this binary outputs this kind of JSON payload. It has a kind exec credential, and it has a status field with a bearer token that it creates, and an expiration timestamp for the token, right? So you can generate any token from your own exec credential executable, which your identity provider understands, and that's it. When you do that, when this executable does that, this request is sent to Kubernetes API server, and then after Kubernetes going to a Kubernetes API server then sends it to our custom auth webhook for validating the token that is being sent. So Kubernetes then sends the request to our custom auth webhook, and the example request first that Kubernetes API server sends looks like this. It contains the API version, the kind that provides in the JSON payload is token review. And then in the spec field, it injects the token that came from the exec credential plugin when the kubectl command was run. As you can see, the token has my bearer token, which was created by the exec credential plugin here in the token field. Then our custom auth webhook actually extracts this token from the token review object and sends this to our identity provider that contains the information for all the users in our company. And then identity provider actually checks with the service directory project permissions and returns back the projects that this user has access to, and then the username also to which this token belongs to. And then the auth webhook sends back the response to Kubernetes API server after authenticating this request. And the example response looks like this. If the request is accepted, then the example response looks like this. It has an API version, kind is again token review. In the status field, it sets the value of authenticated field to true, and it also sends the user meta information with username to which this token belongs to, the UID of the user, and the groups. The groups is actually generated by the auth webhook after reading the project permission from our identity provider. So we just came up with our naming convention that the group name will look like this. The project name, colon, the permission. It can be editor, admin, viewer, however you set up the role binding for your namespace. We'll see that afterwards. After that, if the request is rejected instead of getting allowed, then the response looks like this. It's the same as the allowed response. In the kind, it will be token review, but in the status, it will be authenticated false. And the user will get back this response all the way back to the output of kubectl command that he ran, or the user ran. So this is the custom auth workflow that happens in our cluster, and it happens consistently across all of our clusters. Now, how can we saw that how the example request and response looks like. Now we'll see how to configure this auth webhook with your Kubernetes API server. You just have to pass these two flags, authentication token webhook config file, where you pass a kube config file, and you pass a flag authentication token webhook cache TTL. By default, the value of this TTL is 2 minutes. What this flag does, it sets the timeout for a decision that is taken by the auth webhook. So after that, this decision is not cached anymore. So if you are using a short-lived token, I would suggest reducing it to something like 5 seconds or 10 seconds. Then the kube config file that you pass to the first flag looks like this. It looks exactly like any other kube config file. It has type config. It has clusters array, users array, context, and current context. But the difference is in the cluster server URL, instead of passing it an API server URL, you pass it to the custom auth webhook URL that you built yourself for your organization and you are running. And that's it. After that, your auth webhook is configured, and it can validate your user. The next thing then, after authenticating this request then goes through the Kubernetes RBAC. Now, how does RBAC knows about this request now? So just a quick recap that in the workspace provisioning we saw, the controller created this role binding object in the namespace, right? And the role binding object definition looks like this. It is type role binding. It says the namespace name kubectl that I created. The name of the role binding object is admin, and the role reference here is cluster role admin. So it's referring to cluster role admin, and then it's assigning this role to a group, not any particular user, to a group called kubectl:admin. Okay? So dynamically, every user who will be a part of this kubectl:admin group will have admin access to only to this namespace. Though the cluster role here is admin, but the user will not get this permission on entire cluster. It will be on the namespace itself only, because it's just a role reference and it's a role binding object, not a cluster role binding object. Okay, so this kubectl:admin group that you can see here was actually asserted dynamically on the, in the auth webhook when the request was sent, and this example response was returned back by asserting this kubectl:admin group there. And that's how Kubernetes, this role binding object in the namespace, will authorize this request in the namespace. So this is how Kubernetes RBAC will allow or disallow this request based on if the user has permission in this namespace or not. And then, after passing through Kubernetes RBAC, this request goes through Kubernetes mutating admission webhook. So Kubernetes admission controller provides us a way to define mutation webhooks to intercept any request to your Kubernetes API server, and then you can change the definition of the object or inject new things there based on your organization requirement. So you can customize every payload that gets sent to your cluster. Some example use case of the mutation webhook is you can assign random non-root UIDs, because root UID is vulnerable, and also root UID is injected automatically by Kubernetes if you don't define any. So you can assign or change the UID to some non-random UID based on the namespace in the pod. You can inject environment variables in the pod if the pod does not contain the ones that your organization requires. You can inject some labels on the pod before even the pod. So these things will happen before the pod actually gets created in the mutation webhook. You can also inject init containers or sidecars in your pod definition, even though if your user or developer does not define them in the pod definition. Now we'll see how the example request from Kubernetes API server to this mutation webhook looks like. So the payload will look like this. It will have an UID field, which will just be used for auditing purposes as a reference, and then it will have the resource type. Here I ran kubectl create command, so on the pod creation, so it will say it's a pod, and then the name of the pod that was in the pod definition, and the namespace where the pod is getting created on, and the operation, which operation was made on this. So it was a create operation, as we saw. It can be create, update, or delete based on your kubectl command. And then it also will contain the user information, like which user actually made this request, the UID of the user, and also the groups this user belonged to, which was provided by the auth webhook that we saw in previous slides. And it will also contain the object definition that the user is requesting, right? So after reading this object definition, you can actually analyze the definition and make mutations on top of it to change the definition if you want, or inject new things. And also, if it's an update operation, then you will have an old object field as well, which will show you what was the previous state, so that you can take a diff, and based on that, you can decide. And that's it. That's the example request. The example response will look like this. It will have an UID field, which you will have to populate from the request field so that you can cross-reference them during the auditing. And then you have to pass the allowed field to be true, and you have to pass a patch type that you want to make. Here I'm passing JSON patch, and currently as of now, mutation webhook only supports JSON patches. And then you send a byte array of all your patches, and the patches look like this here underneath. It will have an op field which will say what operation you want to make. I said add, and I pass a path, a JSON path in the JSON definition. It says spec containers 0, which is the first container, and then image pool policy, and the value I'm setting here is always. What this patch will do, in the pod definition we saw, the image pool policy was if not present. That's how I created it. But if it goes to the mutation webhook, after mutation it will turn into always. So this is just one example that you can do. So you can change basically any field in the pod definition or any object definition that will go through the mutation webhook. Now we will see how to configure the mutation webhook with your API server. So you have to pass this enable admission plugins flag in your API server definition binary when you run it, and you have to pass mutating admission webhook option there. That's how you can enable the mutation webhook. And then you have to create a mutating webhook configuration type of object, which will define what are the objects on which this mutation webhook will be applied. Okay? So here I'm passing metadata, pod mutation, and then I define the webhooks configuration, where we'll pass the client config URL, and that will contain the URL to the mutation webhook, where your mutation webhook is actually running and serving requests. And it has failure policy fail. It can also be ignored. So failure policy defines if there is an error in server side or this webhook is not reachable, then what will happen? Will it fail open, or will it actually fail the request? So if you set ignore, then the request will be fail open if mutation webhook is down. If it is fail, then if mutation webhook is down, every pod creation request will fail based on the policy. And you pass the name of the name of the configuration, and also define the rules, like which objects will be applicable for this mutation webhook. Here I'm passing resources pods and the operation type create, which will actually define that only for pod creation request, send the pod creation request to this webhook. And after doing kubectl apply on this webhook configuration, your pod mutation webhook is configured in the cluster. So that's pod mutation webhook, or any mutation webhook that you want for your cluster for any resources, not only just pods. Now, after going through mutation, the request will go through object schema validation internally in Kubernetes admission controller, because you can change any field or definition in the object, right? Then Kubernetes needs to check that if it still complies with the default schema definition of the core objects inside Kubernetes. And after this validation, this request will get forwarded to a validating admission webhook. So it's quite like mutating admission webhook, but validating admission webhook also intercepts the request, but it cannot mutate it. It just validates that if the field values are correct as per your organization requirement. You can check any field, and then you can reject the request based on your requirement if some field has some unexpected value, or if someone is trying to do something differently than your expectation. Some example use cases for using validation webhook is like, you can check legitimacy of the pod or service or object that is being created. For us, we just check if this if this pod is registered, the project this pod belongs to is registered in service catalog or not. Then you can also check like the images that your containers in the pod is that are being used are actually from trusted image registry or not. And based on these decisions, you can actually reject this request immediately before even the pod is created. You can also check the number of containers in the pod, which actually we have tested and found out that large number of containers in one single pod makes some performance degradation for the Docker runtime engine on the host. So you can check that, and if the number of containers in the pod is higher, you can reject that request as well with proper message. Then you can also check the presence of some certain labels or even environment variables if you want that are present on the container or not, or on the pod or not. Also, you can enforce certain best practices for the Kubernetes resource declaration, like how the label keys will look like. You can verify them and validate them. So the example request for the mutation webhook looks exactly same as the validation webhook looks exactly same as the mutation webhook, but the response looks a little bit different. If the request is accepted, then the response looks the following. It has the response field, it has UID, and it will have allowed field set to true, but it will not have the patch field because validation webhook cannot patch object definition. But if it is a deny, if you don't want to allow this request to be accepted, then you can send the response with this UID. You say allowed field to be false, and then in the status field, you can set a custom error code with, for example, this time I'm sending 400 and a custom message why this request will not be accepted, right? So that your user gets a nice feedback that why this pod request is being denied with proper error code and message. So the configuration for validating webhook is same as mutation webhook. You just pass validating admission webhook value in the flag, and then you create a validating webhook configuration instead of a mutating webhook configuration object, and the rest of the definition looks exactly same as the mutation webhook. You can define the rules the same way. After going through validating admission webhook, if the request is denied, you can send right from here a denial message with error code to the user. A full example implementation of Kubernetes validating and mutating admission webhook can be found in this link if you want to go through it. After passing through validating admission webhook, the request actually goes through resource quota controller, which is the last admission control that happens in Kubernetes admission controller. So a quick recap that our automation actually created a resource quota object in the namespace, right? So based on that, resource quota controller will see if it can sustain one more pod in this namespace or not. If it can, then it will allow this request, but if it cannot, then it will reject the request saying, you are out of quota, you cannot create a new pod in this namespace right now. After passing through resource quota controller, after only that, it gets stored in Kubernetes backend storage etcd. At this moment, this pod now exists in Kubernetes etcd cluster. But that does not mean the pod has started running right away. Because after storing it in etcd, then pod security policy, or aka PSP, kicks in. So pod security policies are a cluster-wide resource that manages some security-sensitive information for the containers in your pod. And you can restrict different accesses from your containerized processes using pod security policy. So in order for a pod to actually start, it has to comply with at least one pod security policy that you have in your cluster. Some example use cases of pod security policy are, you can prohibit running a pod with UID 0. So if container breakout happens, it can, so that containerized processes cannot make any harm to your host processes. Because if it runs with root UID and if it has privileged accesses, then it can be dangerous for your cluster. Then you can allow certain or no host path at all to be mounted within your pod, just to be safe and secure so that your pods do not access the host path. Without pod security policy, actually Kubernetes allows you to run any pod as root, which may have root access on your node, because that's the default behavior of any vanilla Kubernetes cluster. So you can restrict these things using pod security policies. Other things you can do is you can forbid access to the host network namespace or host IPC namespace and host PID namespaces, because allowing this will actually allow the containerized process to have almost same level of access to the host processes. And they will be able to sniff into other host processes or other containers running on the same nodes. They will be able to sniff their environment variable or configurations as well if they have this kind of thing, permissions. Or even they will be able to manipulate the network stack as well on your host node where the pod is running. You can also limit Linux capabilities, which are mostly associated with super user permissions like capnet admin or capnet binding, so that what can happen is it may have more privilege escalation permission than it requires, so that what it will be able to do, it will be able to actually escalate privileges to its child processes. I mean, the containerized process will be able to escalate privileges to its child processes more than itself. This can be made limited using the pod security policies, so that you are safe and secure if any container breakout happens. Some more use cases are you can allow a certain range of UIDs and group IDs with which your containers will run with, so that you are 100% sure that it won't be able to use any other UID or GID. And you can also allow certain types of volumes to be used by the pods in your cluster. Like you can define like only allow secret persistent volume config map and download API, or you can also add empty dir, right? So only those volumes will be mountable by your pods in the cluster. And you can also say allow only a certain range of host port access in the host network namespaces. This type of things you can define. Or you can also make root file system inside your container to be read-only, so that container cannot write anything in your namespace. So these are the configurations that you can do. You can enable the admission PSP using passing this flag, and you have to create a default PSP for all the pods in your cluster. You can just create a pod security policy object with restricted name, and then you can fill the the other specs as per the example shown in the link. So I'm not showing them here. And then you will have to create a cluster role and cluster role binding. Here you can see them, so that the service accounts with which your pod will run will be able to use these things. We use this pod security policy. And a cluster role binding will be able to then use this cluster role restricted, and it will be applicable to system service accounts, which is all service accounts in your namespace, in your cluster. And then it will also get applicable to system authenticated, which will be all authenticated users will be able to use this pod security policy. So by default, every pod will run with restricted policy. But if you have a valid use case for your for having privileged pods, then you can create it by creating a privileged PSP and giving some relaxed permission to that PSP, and use it only in certain namespaces with certain service accounts by creating additional cluster role and cluster role binding for privileged PSP. And if multiple pod security policies are there, only the ones that comes the first in the alphabetic order will be used by a pod. This is a tricky one, but that's how it happens for pod security policies. After passing through pod security policy, only then a pod starts actually running, and the user gets the final response back. This is how the entire lifecycle of a kubectl command looks like in all of our Kubernetes clusters in a very consistent way, because these are all automated, not done by hand. Some key takeaways are you can customize your workflow using custom controllers, or maybe using a framework like KubeBuilder to automate any workflow that you have in your organization. Custom controllers are very useful. You can get some example information from there, and you can also reuse your organization's existing permission auth provider using Kubernetes custom webhooks, so that you don't have to implement something new. You can also leverage the admission controllers or webhooks that Kubernetes provides to validate and mutate the resources, so that you know what is happening in your cluster. And finally, take the opportunity to use pod security policies to enforce a secured environment for your workloads to run. Thank you so much. And if you have any question, or if anything looks daunting to you in the slides, we are hiring. You can come to me. I can ensure a smooth onboarding process. Just kidding. I will be here. You can ask more questions here. Thank you so much. The slide links are here if you want to scan, so you can find it from this QR.
We do have 3 minutes if anybody has a question they want to ask.
Sure.
Hi, thanks for your talk. I would like to ask if there was any decision between choosing Auth webhook instead of JSON Web Tokens and using an OECD validation from the AP server, so check the offline signature of the token instead of active validation.
So you're saying what about using OIDC, right? Sorry, it was not clear.
Instead of using an active validation, if you discussed it internally on, and why did you choose active validation instead of offline validation?
Right. So we are using this kind of dynamic behavior because, as we saw, every project gets registered in our service catalog, right? So permissions actually changes dynamically. So if we do offline, then if a project permission changes in a namespace, right, then someone will, the person who will lose the access will have to re-log in to get the new type of permission. If we go through this dynamic workflow, this is how we are actually dynamically giving someone permission or revoking someone's permission. And every kubectl command goes through that workflow. And that's why you saw in the role binding, we gave the permission to a group, not a particular user. So this is why we use this kind of dynamic behavior. Does that answer your question?
Cool. Hello, thank you for this talk. How much of this is open source, especially the service catalog part?
So the thing you saw here, except for the Auth webhook, because the Auth webhook can talk to any identity provider that your organization has, right? Rest of the things are like directly from Kubernetes. The service catalog is not open source, it's just in-house built, but it is only used for the purpose of keeping the service. It has a database and interface, users go there and create a project. And then the username based on our identity provider gets stored there, but this is not something like outside, because this is very tightly coupled with our org structures. So, but yeah, you can have any source right now you have to include with your workflow if you want.
Yeah, I have a very general.
Oh, sorry, one more question. Because the entire thing, I forgot that. The entire thing you saw here, the deployment solution that I mentioned, that goes to multiple clusters, that is open source, and I provided the link there. Yeah, our multi-cluster canary deployment solution is fully open source. Yeah.
Yeah, I have a very general question. Why did you decide to give developers kubectl access in the first place? So why don't you go through some automated process, only let Jenkins do the kubectl applies, but let the developers do it?
Yeah, that's a very nice question. This is kind of like third or fourth iteration of the platform as a service that we are providing right now. And we took that path, that the one that you are suggesting. We came up some kind of magical tooling that will help users to do their job. But the survey does not say that. The reality was not like this. Users are not happy at all when they go through a predefined path, because there is always, like in our Kubernetes clusters, more than thousands of developers actually work every day, and everyone has their specific needs. They see that Kubernetes as an open source project, which has a lot of possibilities, but when you give them a path or a CI pipeline, there you just narrow down the road, right? So then, based on our user feedbacks, the road that we took, or the approach that we took here, we are providing all the features of Kubernetes that Kubernetes provides, but in a controlled fashion, so that users do not feel left out. So this is exactly why. This is based on our user feedback and user requirement in our company.
Okay, and with that, I think we have to stop. Thank you very much, and thank you guys for the great questions. And
I'll be
please
here,
remember
so if
to
you have
rate
any
them on the app.
questions.
Thank you.